All right, so I'm gonna start my demo. I'm gonna be going through this really amazing walkthrough about this reverse engineering challenge for this network services. And the thing that's a little bit different about this week's demonstration in comparison to last week is the different tooling and methodology used to solve the challenge. So I really want to share that so you can sort of see and contrast in terms of what different methodologies and techniques you can apply to these different CTF challenges. So the very first thing is that this challenge is a network service, FTP in particular. And the first steps we can do is that we should connect to it and interact with it to sort of get a feel for how it works, right? That's usually a really good first step. So, we connect to it. So one thing I do want to point out here is that I'm using Netcat in this particular case, but another option is to use the FTP client itself, right? But then, so the question then comes out, what's the difference between Netcat and FTP? And in what situation does one make sense over the other? What kind of different behavior will you get from those two different clients? So that's left as an exercise for the viewer, but there are some differences, right? So we connect and then we get a nice banner from the server. So, a nice thing to run is a help, and you run help and you see very typical commands that FTP support. So in this, the usually workflow of interacting with FTP and these kind of ASCII-based protocols is usually to log in, you use user and then a name of a user. So, I can put Candy, and then you use pass, then specify the password. So let's put foobar. And in this case, right, it gives you the ability of putting in the command user password to log in. And because I didn't give the right credentials, it threw back invalid login credentials, right? So now we sort of know at a very high level what the behavior is sort of like. Another really quick thing we could run is to run strings on the binary itself. And that gives us like, okay, these are all the hard-coded strings here. And that could potentially give us clues in terms of its behavior. So now that we have a high-level understanding of its behavior by interacting with it through network clients, the next step I want to do is to actually reverse engineer it in a disassembler because okay, what we found out with interacting with it dynamically with a client is that it's expecting a password and a username. A password and username, and based off that, then we would get to a different part of the code where we're authenticated and potentially we can get the flag there. So now for us, we need to figure out how to either authenticate correctly or bypass that authentication. So with the first steps in disassembly is to figure out where in the code matches up with that logic of getting the username and the password, and then the mechanism for authenticating. So to sort of quickly go into that place, right? I already jumped to the part of the code, and if you're sort of following along as I'm scrolling, you'll see some of these strings right here. Please enter the password, right? So this is what it is at the assembly block level, right? That IDA gives. This is an interesting thing here where it says, it's looking for this string called blank wall, and then it's doing a comparison with it, right? And then based on the logic of some of these comparison here and function calls, it finally goes into this block here where if you're successful, you get a login. If you're not, you get an invalid login, right? So this is what it looks like in a block diagram for the assembly. But for the Ghidra lovers out there, right, we want the disassembly. And so now we have this nice disassembly, right? And then in the nice disassembly, again, right, it's asking for the password, and then it's checking there, and then check it out. So this looks like this is going to be the username, and then based off of that, it's going to do so it checks the username, and then there's also this comparison with this S variable, and it looks like eventually all that is going to be passed into this function right here. And check it out, this is an if statement. So what it's saying here with this if statement is that it's saying if it's equal to this value, and look, this is like a big negative number, and for us, that's not, usually we like other representations. So check it out. If I change it to hexadecimal, Oh man, okay, let's change. Okay, invert the sign. Okay, there. So what I did there was I change it to hexadecimal, and I invert the sign to make it unsigned. So basically what this is doing, it looks like it's calling this function and it's probably giving the password we gave it. And if this function returns a hexadecimal number that's equal to this value, then we successfully logged in. So now we're getting closer to where we have to look in. And I'm sort of jumping ahead a little bit here, but eventually I'm going to write a script that will brute force the password, but it takes a while. So I'm just going to run it in the background for now. But let's now get back to our reverse engineering, right? So we found the username, and then we found this potential function that we need to sort of figure out, right? So that's going to get our password, do some operations, and then give some kind of a hexadecimal value that needs to be the right value in order to get the successful login. So we jump into the function, and this is what it looks like right here. So what you have here is you start off with a number. So let's jump into hexadecimal. So hexadecimal, so 1505. It starts with a value, and then based on that value, it does a for loop, and then it just does mathematical operations. So this is what the decompiler this is what the decompiler says it is, right? So you're adding variables to offsets, and so that's a for loop, and then here is the operation itself. So it looks like addition with multiplications. That's basically what it is. For loops, adding, and then multiplication. So the approach that we're going to take this time is we're going to actually implement this in our own script. So this looks like some kind of hashing function, right? We're given a seeded value and also our input for our password. It's going to do some mathematical operations of it, and then it's going to return the value. And what's funny is that usually the compiler is the easier way of understanding and then representing it. But in this case, funny enough, I'm going to use the, okay, so this function is 40154. So that is here. So this is the actual mathematical operation. And so this is sort of the interesting thing about reverse engineering. So what we have here is the block representation of the assembly. And previously, I showed you the C decompiled version. So now for what we need, actually, the listing. So this is the listing of the assembly code itself, right? And from it, basically what it's doing, so we're trying to figure out all the mathematical operations we have to extract out of this and then implement it within our own script. Basically what it's doing here, it's shift lefting. So there's some register value here, and then it's going to shift left by 5. And then the other thing is going to add this value in RDX, which is an offset into some memory location. So what's funny is that if you parse this, and then so I'm going to jump to the actual code where we actually encode this right in the script. So this is what it ends up being in the script here, right? So what we did here was that we understood it from the assembly level, and then now we're going in, to write that as a script. So basically what it's doing again, so we're getting this, shift 5, and then we're adding it with some start variable, and then we're going to do it as a for loop for all of the bytes in this sort of array here. And again, so this is what it is in a nutshell. So let's run this script really quick to sort of see it in operation. Boom. So basically it for loops throughout that password value, and then it hashes all these different values, and then this is a final hash value that it eventually returns to the calling function, right? So what we did here was that we implemented that hashing within our script. That's step number 1. The way to verify this, and for the sake of time, I'm not going to have time to run the debugger. So the way to verify this is what I would do would be I would run a debugger such as GDB. So I would run like GDB FTP, and then based in this debugger, I would put breakpoints in this hashing function where it actually operates, and then I would put in my input, right, which is a foo bar, my password, and then put a breakpoint on where it calculates it. and then I would verify it with the output that I had for my run here. And if I get the same values for in the debugger as I do for my runs here, then I knew that my implementation of my script is correct, right? So that's what we're doing there. And if we jump back to the debugger really quick, if we remember, what we want to do is we want to get this value here, right? So we want to put in passwords, have our hash function go, and then get this value. Because if we get this value, we know we got the right password. So that's what so that's going to be our approach for our final script. So this is implemented here. So how the script works is that, so if you remember, this is the final hexadecimal value right here, right? If you remember back from our disassembly, right? D309. So we go back here, right? D309. So this is what we're trying to get. These are all the different values in the alphabet, right? So this is what we're going to use. And if you remember previously from the first script that was written, right? It was an implementation of that hashing function, and that's what this is right here. This is the hashing function. And then so what we're doing here is we're using the itertools module of Python, and we are going, in this case, we're going to create a string of 6 characters, and it's going basically to brute force all of the different possibilities of 6 characters from this alphabet that we give it. And it's going to run this hashing algorithm, and it's going to check if the output is equal to our target here, this hexadecimal value. And if so, then it's we're doing the if statement. If so, then we found it, right? So basically, we're brute forcing. That's what we're doing. We're brute forcing all the possible 6-character alphabet values, and if the output of that equals to our target hex value, then we knew we found the right password. And I ran that in the background. It takes quite a bit of time, but basically we brute force it, and then we found that the answer is cookie. So that's what that is. And the author of this walkthrough, the way he did it initially was he tried different values here for the length of the password. First he tried 4, 5, and then when he did it for 6, it got the right password, right? So that is the answer script, the solution script to brute force the password. So now let's actually run it to see if it will actually work, right? So we netcap to the service here. So let me see what the actual port is. Netcat 127.0.0.1.120.12. And user. And again, if we remember back from our reverse engineering here, right? Escape. The username that expecting is blank wall. We got this from the disassembler. So blank wall, and then the password is cookie. We do it, and eureka, we're logged in. So we're logged in, but where's the flag? So what we did here is we got further along in the challenge, but now we have to figure out the next part of the challenge, which is how do we get the flag? So this is where we could jump back to our reverse engineering again. And then from here, we're gonna have to figure out, is there some aspects in the disassembly that will give us a clue for where the flag could potentially be, right? And let's see, in this disassembly, these are all the possible functions. The way I would approach it, so what I did there was that, okay, here it is. So let's go back to, so basically in this really messy data structure, what this looks like is, it looks like it's a decision tree. So it looks like it's probably either a chain of if statement or a switch statement, where depending on the command that the user gave, it will then branch to a function to handle that command. So for instance, we have these different command, user, pass, help, right? So that's what this data structure is. And the answer that, or the part that we're gonna look for, is a command that will potentially give us the flag. So the approach I took was that I looked for the reference of the place that calls the user authentication, and based on that user authentication, right, then after that would be a potential place where following code might be called to actually get to the place where I could potentially get the flag. So basically, if you look through these different parts, so there's different commands like pw, cwd. Let's try those commands, just for the heck of it, right? So we jump back here, pwd. So basically what happened there was that the session timed out, right? So again, we have to log in, blank wall, password is cookie. So we do something like pwd. It's like send user for, oops, looks like I did not put the user command with my username. So then pass cookie, and if I run help, so pwd, so it tells me the present working directory, and I think cwd will do the same thing, or directory change. So so that's change working directory. Okay. So again, so that kind of shows you I found commands with the reverse engineering, and then by finding that, then I test them out. So a really interesting command from our disassembly here is that we have this RFD. So let's try to look at what the logic here is. RFD, right? So it looks like command not found. So one branch is command not found. Other branch is that it will go down here and then it will call this thing. So check it out. So it looks like what it does here is like if we run that RDF, it's going to do something. It's going to open this file called r-solution, and then it looks like if this doesn't exist, it errors out that the flag wasn't there. Otherwise, looks like it's going to read from that file. So let's try that RDF command and see what happens. So RDF, we run it. Oh, it timed out again. So really annoying with some of these challenges sometimes, where if you don't do it fast enough, it kicks you out. So cookie, and then RDF, and then we get our flag. Jackpot, right? So very cool. But so what I sort of really want to emphasize is that throughout this demo, we ran into different obstacles and different challenges, and then we had to figure out, okay, what is the right approach and technique and methodology we can use to find the answers to the obstacles and challenges we ran into, right? So anything else I wanted to share? So okay, I wanted to compare and contrast this to the technique that I used last week. So there are a lot of similarities between what I did this week and last week. The similarity was that I had to figure out what the hashing function, how it worked, and then I had to encode the hashing function. Last week, I had it encoded in a format that the Z3 library could understand, which in that case was the SMT2 format. So I had to specify it in this really weird format that you're not used to, right? You have to sort of research. So I had to encode it in that format. This week, all I had to do was I had to encode that within encode one. I had encoded within just Python, right? So I just use Python notation to encode the hashing function. And then in last week, I encoded within that SMT format in order that Z3 can then use its solving equation libraries to solve it. So Z3 library use its techniques to solve it for me. This week, what I did was that let's check out my Python script here. What I did this time was like I brute forced it, right? So I implemented the hashing function, and then I used some other libraries in Python in order to brute force it. So that's sort of the high level difference in terms of approach for the techniques from this week and last week. There are other very powerful techniques, such as using the Anger library, but I feel like that's kind of cheating in terms of, because with Anger, you only have to use 3 lines of Python code to solve it. And then, so if someone hears that, they would automatically, okay, I'm just going to use that. But I think the right approach in terms of actually learning how all these different approaches work is to first start with the manual stuff and do these manual processes to understand how it actually works in the background. And once you master and really understand how it works, the nitty gritty of it, then you can then use the more powerful libraries such as anger, so you can understand what's happening in the background. Otherwise, when you run into problems, you're not gonna be able to sort of troubleshoot it and use those tools to their maximum potential, right? So that's sort of the workflow I really recommend users to follow. The other thing I wanted to share about CTF in general, so in this case, this challenge is in the reverse engineering categories. Two of the big categories in CTF is pwn categories and reverse engineering categories. So what are the difference there, right? In both of those categories, you have to do a lot of reverse engineering. But in the pwn category, usually the goal there is that there's some vulnerability, usually memory management, but something in that category where you eventually get remote code execution. So you sort of try to find the vulnerability to get remote code execution, and then you use that to actually finally get the flag once you get code execution, the ability to have code execution. In reverse engineering here, usually the goal here is to understand the different mechanisms within the binary itself. So we have to figure out some functionality, reverse engineer that functionality, and then leverage our understanding of that functionality to get the flag. So this is really important here. This is sort of a really big takeaway here. So, you know, why were we able to authenticate here, right? So number one was that the value, if we go jump back here into the pseudocode, the number one was that here was the value that needed to evaluate to true. So it's sort of a simplistic number. It's basically just a number. And then the function, all the operations you sort of use to churn through your password to get to here, it's not that complicated. So we were able to encode this and run it ourselves. And because and luckily for us in this case, the password space wasn't that big, so it was only 6 characters. So based on the limited size of the password, the simplicity of the function, and then it was just based on hard-coded values here in terms of, you know, this is what needed to be evaluated to true. So we had all the pieces that we needed to crunch out the right numbers to get the final solution, right? So that's the takeaway here, and this is why we're able to get the right password. So I think those were all sort of the big points I wanted to cover with this walkthrough for this CTF challenge. Any questions, comments?
So I guess my biggest question is that could you then take the brute force once you found the hash, right? The hash that's encrypted and you found the string. Mm-hmm. Can you then feed the output of that into your FTP session? Right. So that it automatically tries the username password as your
that is so okay. So for some CTF challenge, that is what you have to do. There are CTF challenges that are structured that way, where you sort of have to feed the server the values that you come up with, right, in order for you to sort of get to the next phase or verify that your hash is right or not. And so that's one approach. If you weren't able to, that would be an approach if you were not able to reverse engineer the hashing function itself, right? But then you have to think about why you would want to sort of use that approach, the one that you shared, versus encoding it yourself. And also the approach you sort of shared, that is an approach that pen testers use to brute force passwords, where they don't have the algorithm. They don't know how the hashing works, right? In those cases, that's called an online brute forcing, where you just premutate a lot of passwords and then you send it to the server and then you wait for the server to give you success, right? The biggest limitation there is depending on your connection with the server. One is speed, and if there's some kind of lockout mechanism, you could get locked out, right? Where like the server will only allow you so many numbers of tries, and it locks you out. So those are the disadvantages of potentially running it against the server itself. But you, in some use cases, though, you will have to, if you don't have the information to reverse engineer and encode the function yourself, so you can do it on your own machine.
Very cool. Very
Yeah.
cool.
Yeah.
There's definitely a lot to unpack here. Um, and I think one of the things that I would first, want to know is, so to get to this point where you're actively writing a script,
Hmm.
um, does that just comes from understanding what's in the disassembly,
Yeah.
and then understanding that if you can just dissect that single piece and
Yeah.
implement it in something that's easy to understand, like the Python,
Yes.
then you can start doing the interesting things like eventually getting the password.
Yes, exactly that's the exact process that I'm trying to emphasize here. And but then there's a lot of implied issues with the points that you're bringing up, though. Like for me right now, currently, to be honest, I am like semi. I maybe my confidence level of doing this kind of stuff is around 30 to 40% right now, right?
Okay.
And honestly, because I believe if I practice this more, that confidence will rise, right? But in my early career of doing CTF, in a lot of cases, I'm not confident. I was not confident enough to do this because one of my fear is that. Your line of questioning is sort of arising this very important part where, luckily in this case, this function is isolated enough where it's sort of an isolated black box enough where it's just all you need here is a password. So based on a password, you have all the information you need. In other cases, there's a huge line of dependencies where potentially, say, this function is grabbing for information from the environment variable that potentially we don't have, and then it might be dependent on other potential global variables that are updated based on other functions that we don't understand good enough to know what are these values for these either global variables or environment variables that will affect the operation of this function, right? So if you don't have that kind of, if that was the level of dependency that was required for this function, then potentially we don't have enough understanding of it. And this is where your initial strategy of doing it directly with the server makes more sense, because we don't have enough understanding of the function itself to encode it ourselves. So we have to use the actual network service itself to verify those values, right? So in those cases, the player will not be confident enough to encode it. So that's a big requirement here to be able to encode these kind of functions, is to have that confidence to know, okay, I know this is isolated enough, self-contained enough, that my script here does the exact same thing in the actual challenge binary itself. So yeah, really good points.
One,
Anything? Oh, please, yeah.
yeah, just one last. So in your previous videos, I've also seen you using the same setup as well, and I just wanted to comment on it.
Go on.
It looks like you're using that 2008 server, right?
Yes.
To run IDA and do your
Yeah.
disassembly.
Yeah.
Is that the best use case for IDA? Is that the best use case for a disassembly environment? Do you have a Windows computer? Can I use something else? I used Gadira directly on my Fedora desktop.
Mm-hmm.
Do I need to go out and maybe think about standing up a Windows environment? I mean,
Okay.
because I'm seeing this and I'm thinking, wow, is there something that I'm missing about why Candy setup is better than, say my setup, right?
Yeah. No, these are really good questions. So, okay. The reason because I have my current setup the way it is because it works for me, and I don't think my current setup with IDA on this VM, it's not the best. It's just it worked for me, and then therefore I just use it because it works for me, right? Right now, my host system is a Mac OS because my workflow. I'm just comfortable with it, but I know other people who use IDA Pro directly on Mac OS. So what's funny enough, this is going to show my age, but when I got into disassembly, back in the days, IDA would work best within Windows. And as a force of habit, I'm just sort of a little bit like you're saying, you're just very comfortable with Fedora, so you use Fedora as your base distro, right? For me, my old habit was that IDA in the past worked best on Windows, and then therefore, based on that conditioning, that's why I use it on Windows, right? It's just based on that conditioning. And then in the past, also, most of my disassembly were on Windows binary itself. So then I thought, okay, if it's going to be, most of my disassembly is on Windows binary, then I should probably have the disassembler on a Windows VM itself. But in modern days now, I see people use IDA on all types of operating systems. You know, Mac OS, Linux. They do use it in those use cases. So I don't believe that this is probably the best. And I haven't done enough research myself to know the benefits of one or the other. So currently, it's just because I have a working setup, honestly, right?
Sure.
So yeah, that's sort of my situation. I just and the other thing is that the IDA license is like crazy expensive, and unfortunately, back in the days when you bought IDA, you could use it on all of the different operating systems such as Linux and Windows. But now, freaking IDA, they limit you. Like if you buy a license for Windows, you're stuck with Windows. So that's a really bummer because yeah, something like Ghidra, I think you can use it on all operating systems, I believe. So that's really nice.
Yes,
yeah.
you can. Anything Java, it'll play.
Yeah. And then so you bring up the questions about why the disassemblers, right? So for me, it's just I'm just funny enough I was used to it, and then this week recently I've been doing a lot of disassembly within a very old version of Binary Ninja, which I personally really like. But because my version is really old, like some of the really nice perks that you see here, you see how it automatically gives you the text string of these variables, right? This version of IDA does that really good for me. And my old version of Binary Ninja, unfortunately, it does it very hit and miss, where it does it for some, but for others, it doesn't do this. So, I showed you how I was able to find that command RDF. IDA gives that to me automatically. Within the old version of Binary Ninja I had to click on the variable, and then it would bring me to the actual string. So for an operator, if you don't do that, you might miss it, right? So that's why for this demo, initially I wanted to do with Binary Ninja, but because it didn't show these strings automatically, I had to end up using IDA. And then funny enough, it's like, okay, unfortunately, some stuff in IDA is better than in Binary Ninja for the version I have. So for this demo, I had to use IDA, even though I wanted to use Binary Ninja. So, but again, you need to sort of play around with these different tools and then figure out in what use cases where does one make sense, where does one really shine, and where one really doesn't, and that will help you pick the right tool for the right job. Because unfortunately, people get into these holy wars and then they miss out on potentially a really good feature that would make their job much easier or give them what they need to solve problems that if they were just too fixated, like, I'm only going to use IDA for all my solutions, you might be missing out on a lot potentially.
Okay. Well,
okay.
Thank you. Yeah.
Oh,
that was
cool.
great.
Yeah, definitely. Let's